All right, hey everyone. So here is our first lesson. This will be taught for group 1 on Monday, September 21st. So group 2 students and then group 1 kids if you're gone on Monday. Here is your lecture. So today we're going to move on. We're still sticking with motion and stuff. We're going to kind of up the ante a little bit and do something called kinematic motion. Okay. Um, so right now with just our basic motion, okay, we have kind of just one of three ways in which we can describe how an object moves. We have our speed, distance over time, our velocity is our change in distance or displacement over time, and our acceleration is our change in velocity over time. Okay. These three ways are very limited, especially as you saw in the quiz for one of the questions. It's like, if I don't have every bit of this information, it's very hard to use these equations, and I have to use like multiple steps and whatnot. Okay, so what we do in physics, kind of help that out, is we have these kind of four equations that are all derived from either velocity equals distance over time, or displacement over time, sorry, and your acceleration is change of velocity over time. Speed kind of gets left by the wayside. Honest to goodness, after the test over motion, speed now becomes velocity. Okay, so like on homework and stuff and in class, you'll hear me say speed and velocity, and they're basically interchangeable. Which I know can get kind of confusing, but that's just we in the realm of physics we don't really talk about speed very often because since it's a scalar quantity, it just doesn't make a lot of sense to ever really bring it up in the day-to-day life. So we just kind of ignore it a little bit. Okay, so anyway, let's get after it. I could derive out, kind of show you where these equations come from. I've done it in the past, and honest to God, I don't do anything with it. It's more of just a way to show that I'm smart, which you guys don't care about. So there's four of them. Okay. I'm gonna list them in kind of no really particular order. I will say the fourth one is one that's not used very often. Okay. But it looks something like this. Okay, so the first one is V final equals V initial plus AT. The second one is change in X equals V initial T plus 1/2 AT squared. And the third one is your V final squared equals V initial squared plus 2A delta X. And then lastly, this last one, like I said, not used very often, but is still viable. And that is delta X equals the quantity V initial plus V final times time. Okay? So, now each of these equations has kind of a marker to say if it's useful or not. What I mean by that is if we take a look at this very first equation, okay, you notice that in this entire equation, what's one thing it doesn't have? Well, it doesn't have displacement. So I'm going to say doesn't have delta x. Okay, so what does that mean? Well, what it basically means is if you're looking to find displacement, you probably aren't going to use this equation, right? This next one, well, this time it doesn't have V final. So if you're trying to figure out how fast something's going after a certain amount of time, that's not this one. Okay, there's no V final. This third one doesn't have time. If I can spell time right, that's time. Terrible spelling, I know. And this last one doesn't have acceleration. Okay? So, once again, all this is stating is these equations, these are the variables it does not include, meaning, like I said, if you have a question where you're trying to find your delta x, trying to figure out how far something went, this is not the play. This first one is not the play, okay? Second and third one are probably what you're going to most likely use. This fourth one, like I said, it's not used very often, okay? It's kind of a special case one, so like has to follow this parameter. So this fourth one can only really be used, and it makes sense if there's no acceleration. Object moving at constant velocity. Okay, that's kind of the only time this fourth one can be used, when objects moving at constant velocity. Okay. Now, all of these things, okay, are x-axis. Okay, so moving to the left or to the right. Okay, as mentioned, if you look, all these things are vector quantities. Minus time is scalar. V final, velocity is a scalar or vector. Initial velocity, vector. Displacement, vector. Acceleration, vector. So now we have, okay, this xy. So all this stuff right here is your x-axis. So what does y-axis look like? Well, not really different. They are literally the exact same equations. I'm just going to add little y's on all of this vector quantities. So v final y equals v initial y plus ayt. Delta y equals v initial yt plus 1/2 ayt squared. V final y squared equals v initial y squared plus 2 ay delta y. And the last one, delta y, is equal to v initial y plus v final y t. Okay? And that's it. It's the same exact equations. We just throw little subscript y's to indicate if something is moving up or down. Okay. Now, when I say up or down, okay, currently this is all dictating an object is like driving north or driving south or moving up or moving down. It's like objects are still sticking to the ground. Okay, so nothing's flying in the air right now. Okay, with these situation setups. Okay. So, how can we use one of these equations? Well, let's take a look at an example. Okay, so let's say good old Bubba. Okay, so let's say Bubba starts from rest and sprints 40 meters with an acceleration of 3.2 meters per second squared. How fast is he moving at the, oopsies, lost the screen. Sorry, how fast is he moving at the 40-meter mark? Okay. Now, if we are using these first bit of equations, okay, the biggest thing we don't have is time. So we kind of like do a quasi-solve for time thing, which doesn't really work out super well. Okay. So let's kind of take a look at this. let's use a kinematic. Well, I'm just going to start by listing off what I know. Now, some of those stuff for some of you still might be very easy, very straightforward, but I do highly recommend kind of one of the first steps you can take is kind of list what do I know, what I don't know. So I'm just going to say know and unknown. I should probably put that on that. Known and unknown. Okay, so what do I know? I know my V initial is 0. I know my delta X is 40 meters. I'm using X because I don't really indicate which direction he's going, so it's kind of just a good assumption saying he's moving left or right. In this case, right, because it's all positive. But you could say delta Y if you really wanted to. Then I'm going to say A is equal to 3.2 meters per second squared. Unknown, V final is my unknown. Okay? So, now kind of comes the tricky part. Okay? Part students struggle with is, okay, I have all these variables down low, and now I need to figure out which one of these equations is it going to be. Well, the way I kind of always look at it is based off of my unknown. Okay, the thing I want to solve for. Okay? That's my first step. So, for example, I want to find final velocity. Okay, let's take a look at this first equation. So, first equation, hey, it has final velocity in it. But it does not have displacement in it, no x, see? And also has time. And I don't know time. I could solve for time, sure. That's a lot of extra effort, though. So first one doesn't work, okay? Second one, okay, has delta x, but does not have v final in it. Okay, so look, no v final. So second one's out now. Okay. Third one, hey, has v final. Sweet. Hey, has v initial. I have that. Has acceleration, has displacement. So it has all my stuff. Okay, I need to find v final and all this stuff I have. Okay, so maybe number 3. Number 4, nope, can't do it because I don't have time. So number 3 is my option. Okay, so I'm going to say, show me the screen. V final squared equals V initial squared plus 2a delta x. All right. So I want to find this one, so I'm going to leave it there. Equals 0. 0 squared, always 0. Plus 2 times 3.2 times 40. Okay. So get the old calculator out. Bop. Okay, 2 times 3.2 times 40. So I have V final squared is equal to 256. And then because it's squared, square root both sides. Bop, bop, bop. So square root of my answer gives me even 16. V final is even 16 meters per second. And I did not even plan that one out. Awesome. Got a nice number there. Okay. So, all right, pretty straightforward. Let's take a look at another example. Okay. So it's gonna be Bubba based. Okay, but let's say Bubba is heading south with a velocity of 14 meters per second. And he begins to slow down with an acceleration of 0.5 meters per second squared. If the slowdown takes